All right, so today we're doing topic 13, which is central limit theorem and confidence intervals. Although this is the topic, I have rearranged it a little bit because I do think in another way this makes a little bit more sense. So actually what we're going to be covering is more specifically get into statistical tests. I feel like the end of last topic just feeds nicely into this to begin with. Then we'll go into central limit theorem and then confidence intervals. To begin, before we get started, again, I want to reiterate that statistics is pretty heavy. So if you really want to narrow down and take a little bit more chill, which is absolutely fine. If there's a time to take it chill, it would be now. Take a look at this concept questions doc, which I've linked in your homeroom here. Take a look at this concept questions doc. And as we make our way through the material, you should be able to slowly check off these questions. And then at the very end, when we get into our linear regression, you'll be able to answer these as well. So the whole of phase 2, as long as you can answer these questions conceptually, I would say even like copy down these questions and like write your own answers to these as we're going through them. These are the questions that come up most during interviews that are related to stats. And anything else, they're either very related to these questions or wild cards. So yeah, use that to help prioritize what material is important or not, because there are a lot of labs there. Something else that's going to be helpful, because we're actually going to start talking about statistical tests. I've also linked down here, I've added these to the phase 2 resources, and this is the same one that this concept questions link is the same one that we have here. I've also put up a summary of statistical tests as a PDF. This is just every statistical test that we're going to talk about in the next couple of weeks. So today we're going to actually start with this first one, a one sample. I don't know why it's blurry now, but feel free to download this PDF. We're starting with a one sample Z test. So that's what we're going to start with. And that's today. And all of these are coming in the next couple of weeks. So if you just want to see like a one-stop shop of like all of the stuff summarized and also links to the relevant things that you need to use to calculate these, here's where you can find it. All right, so this is what we're going to talk about. Let's do a statistical test to begin. And to start, this is what a statistical testing situation looks like. So let's read through this. So a data scientist wants to examine if there's an effect on IQ scores when using tutors. To analyze this, she conducts IQ tests on a sample of 40 students and wants to compare her students' IQ to the general population IQ. So the way an IQ score is structured, we know that a standardized IQ test has a mean of 100 and a standard deviation of 16. When she tests her group of students, however, she gets an average IQ of 103. Based on this finding, does tutoring have an effect? So here what we're doing is we're doing a statistical test. More specifically, we're going to be doing a one sample Z test, and I will talk a little bit more later about what conditions will tell you what test to perform. In this case, we know that everyone in the world on average has a mean IQ of 100 and a standard deviation of 16. We're seeing, compared to the general population, is this class of 40 students, if they average out to 103, does tutoring make them significantly smarter? That's what we're trying to figure out. Any questions on this setup? All right. So before we get into actually conducting the test, let's go through a series of steps. And these steps do apply to every single statistical test. So 6 main steps. First, you're going to set up your hypotheses, and we're going to talk about each of these in detail in a little bit. Then we're going to pick our statistical test based on our experiment. Then we pick an alpha, calculate a test statistic, find your p-value, and interpret. And we're going to go through all of these steps for, I think, almost all of the tests that I have listed here. So yeah, cool. So the first step is setting up a hypothesis. And if you're familiar with, like, I guess if you've done any sort of statistical testing before, or if you've done like science experiments, you always have a hypothesis about what you think is going to happen. So every experiment starts with a null and alternative hypothesis. Typically, a null hypothesis represents no effect, and an alternate hypothesis represents what there is an effect. So in this case, this is how we notate our hypotheses. Let me draw some boxes here. So this is how we notate our hypotheses. H0 stands for null hypothesis, and it's just saying that X bar, which is the average of those 40 students who were tutoring, is actually just the same as the population average, which is 100. So this null hypothesis here is just saying, sure, the 103 is a little bit higher, but in the grand scheme of looking at the context of the population, 103 is pretty much 100. It's just like maybe a little fluke that a couple students have a slightly higher IQ, but tutoring, you can't definitively say has an effect. In this case, we have an alternate hypothesis, which is usually denoted either HA for alternate or H1 also can be used. And this is saying that X bar, which is the 103 average, is greater than mu. Actually, this should not be greater than equal to, this should be strictly greater than. So basically what we're saying is this group of 40 students and their average IQ of 103, is this significantly different from 100? Of course, if we just look at the two numbers, 103 versus 100, sure, yeah, 103 is bigger. But what are the chances that the tutoring actually has had a definitive effect? Not just by chance you picked up, you just so happen to pick like smarter students to begin with. That's what we're trying to calculate. If you remember what we were talking about last time, the standard deviation does matter. Remember how we were talking about when we had like different curves, and even though you have the same score, if different curves have different standard deviation, the effect is different. That's very similar to what we're going to take a look at. Here we have a standard deviation of 16. So if the standard deviation is 16, meaning that on average, the distance, or on average, people's IQ scores are about 16 plus minus 16 away from the mean, which is 100. So 66% of people fall between plus minus 16 of 100. So that means 66% of the population has an IQ between, 84 and 116. With a standard deviation of 16, you can see that, all right, then maybe 103 is not that big of a difference. If their standard deviation was 1, just as an example, meaning that 66% of the population has an IQ between 99 and 101. So that just that small little sliver, 103 will be a lot more impactful. So that's what we're trying to use to calculate. So going back to hypotheses, null hypothesis represents no effect. Alternate hypothesis is the case where you do have an effect. And in this case, I need to change this, but in this case, it should be strictly larger than. Okay, so we'll see some other examples later on, but another question to ask yourself when setting up a hypothesis is the test a one-tailed or a two-tailed test? In this case, it's a one-tailed test because we're taking a look to see whether an IQ is greater than. An example of a two-tailed test is you just don't know what the effect of tutoring might be. It could be up or down. So if you think that the number could go either up or down, it becomes a two-tailed test. But in this case, because we only care about the increase, it becomes one-tailed. So based on these hypotheses, for tutoring to have an effect, we want to reject the null hypothesis. So we want to reject this first hypothesis that we had, which is that the 103 IQ is equal to the 100 population mean. You actually never say except the null hypothesis. I don't know why that is. And you never say except the alternate hypothesis. When you're talking about hypothesis testing in statistics, you always say reject or fail to reject. So basically, if tutoring has an effect, we reject the null hypothesis. But if tutoring does not have an effect, we fail to reject the null hypothesis. This is more terminology. But yeah, that's just more context setup. All right. And just to recap, these are our numbers, our population info. We have a mean of 100 and a standard deviation of 16. And in our sample, X bar is 103, those 40 students that were tutored. have an average IQ of 103, and there are 40 students. So that's step one, just setting up our hypothesis, really just writing this last line out. Okay. Steps 2 and 3 are picking the test and your alpha. So first, picking the test. So this is the first test that we're doing in this course, and it is a one sample Z test. The conditions for performing a one sample Z test is if you know the population mean and standard deviation, you can conduct a one sample Z test. So in this case, we do know that the population mean of IQs is 100 for the mean and then 16 for the standard deviation. So we know that information, therefore we can conduct a one sample Z test. In other situations, you'll see that we don't have the standard deviation, and so we'll do a different test. So that's picking the test. The next thing we have to do is select our alpha. And alpha is something that you select before you even conduct the experiment. So alpha is your cutoff value. It is the threshold for rejecting your null hypothesis, and it is typically set at 0.05. Another way of saying alpha is by using the term or phrase confidence level, which is 1 minus alpha. So we're looking for an alpha typically set at 0.05. Another way of saying this is with a confidence level of 95%, we can reject or fail to reject the null hypothesis that blah, blah, blah. So interchangeable terms, kind of, just remember one is 1 minus, but alpha is typically set at 0.05. We'll take a look and see later. If you have a smaller alpha, it makes it harder to confirm that there is an impact of tutoring. We'll take a look at that in a little bit. So that's step 2 and 3. Questions here? We haven't even conducted the test yet. We're just setting everything up. Okay. So next, we're going to conduct the test. And to conduct a one sample Z test, we're going to make use of a test statistic and a p-value. There's a lot of stuff going on here, but let's take a look. So for a Z test, and for every statistical test, there's an associated test statistic that will give you an idea of what you're testing. In the table that I have here, you can see that there's a column called test statistic, and every statistical test does have a test statistic. So the test statistic is calculated using this formula here. X bar minus mu divided by sigma divided by the square root of n. Don't have to remember any of these formulas. All the formulas will be given to you here. And if you ever have to do this, you can look up the formula. So with this, we're going to calculate our test statistic. And for this group that we're testing, the test statistic turns out to be 1.19. Just plugging in all of our numbers, with our mu and sigma being 116 and our sample data being 103 for X bar, n equals 40. Just plugging in all the numbers here, you end up with 1.19. The next step that we do here is, okay, 1.19, what does this actually mean? 1.19 actually means that the value of 103 is 1.19 standard deviations away from the mean and to the right of the mean. And I have a diagram to explain that in a little bit later. After you have a test statistic, the next thing you have to do is look up the associated probability from the Z table. And in this case, I've linked the Z table here. And the Z table, we talked about this very briefly at the end of the last session. From the Z table, we can figure out the probability or p-value associated with this. So back to the slide. Based on this 1.19, we can look it up here. 1.1, and then 9 is all the way at the end here. 1.19. Our associated p-value or probability is 0.883. Cool. For a right-tailed test, oh, actually before that, 0.883 is just saying that the average IQ of the tutored students, of the 40 tutored students that we had, is greater than 88% of the population. So sure, we had that average, that was 100. That average IQ of 103 is greater than 88% of the population, which sounds pretty promising, right? So for a right-tailed test, and you don't really have to remember this step as much, I'll have a diagram that'll make it easier to understand. p-value, you have to take 1 minus. And so in this case, the p-value is 0.12, which is greater than our alpha of 0.05. So the purpose of getting a p-value is to compare that to our alpha value to determine whether we reject or not reject our null hypothesis. Let's take a look at the diagram because I think that'll make it easier to understand. Okay, so this is our standard normal distribution. We're standard at 0 with a standard deviation of 1. So if you remember, when you turn anything from a normal distribution to a standard normal distribution, it allows you to make comparisons. So here we have the line between red and blue. That's actually 1.19, roughly 1.19, which is a test statistic calculated from here. So that means if we were to translate this into our population distribution, let me just annotate this. Hold on, let me find a good color. Okay. So if instead of standard normal distribution, this was our full distribution, this could be a mean of 100. Actually, let me use a thicker pen. Okay. All right, so in our original distribution, this would have a mean of 100 and a standard deviation of 16. And then this line over here would be 103. So here is our 103. Compared to that, this is where alpha is. So alpha, which is 0.05, and what 0.05 alpha means is that wherever alpha is to the right of it or the outside of it, this probability is 0.05. So this combines a lot of things that we talked about last time. One, this is our probability density function. And also the area under this whole thing does sum up to 1. And so this is our critical value, our alpha value, where the area there is 0.05. And so what this critical value means is that if 103 falls into this region here, then tutoring has an effect. But if it doesn't, tutoring does not have an effect. So to go into a little bit more detail, combining some of the things that we talked about in the last slide as well, this area here is 0.05, 5%. We had a p-value of, just to go back real quick, we had a p-value of 0.12, which means that this area here, being this blue area here, this area is 0.12. So just by drawing it on a diagram and like comparing these areas and like thresholds and all that, we can see that this 0.12 area falls within the, or it falls inside of alpha, if that makes sense. Basically, alpha shows significant differences. Anything to the right of alpha is significant differences, and anything to the left of alpha means not significant enough. So therefore, based on all of these, we're concluding that tutoring in this case, even though all the students had a slightly higher IQ than the average of 100, tutoring unfortunately did not have an effect here. And we made this conclusion a couple ways. One, we compared p-values. We compared our 0.12 to 0.05. Usually, if your p-value is larger, it's not as good. One way to, I think we're going to get into p-values a little bit, but one way you can interpret p-value is that there's a 12% chance, 0.12, there's a 12% chance that this 103 IQ occurred by chance, just by random. And you don't want it to be more significant randomly. You want it to be more certain that it's more significant, if that makes sense. We'll get into p-values in a little bit. Another way we compared this is we also looked at alpha on the graph. So if you can reverse alpha and figure out what is the statistic associated with alpha, which we can actually do here, if we look up 0.95, we can actually reverse engineer the alpha associated. So it would be roughly 1.64 or 1.65. Oops. What that means is this alpha has an associated z-score of 1 point, what did I say? 1.65, 1.65. And because this was 1.65, and then this line here is 1.19, 1.19 basically did not make it past the threshold for tutoring to have an effect. A lot of stuff just happened. Any questions about any of that?
Yeah, I had a question. Just to go back to what you said. The larger the p-value, that if it's larger than the
alpha value.
Yeah, if it's larger than 0.05, that signifies what again?
So if your p-value is larger than your alpha, it signifies that your alternate hypothesis is probably not true.
Okay.
Yeah, that's another way of looking at it. And in this case, our alternate hypothesis was, yes, tutoring does have an effect. So in this case, in this scenario, tutoring did not have enough of a significant effect.
Oh, okay.
You're welcome. Anything else? This is very confusing. I know. I think like in college, we spent like 2 weeks talking about this, where we were spending like less than an hour. So feel free to let me know if there's anything that you need to clarify, but also in good news, we never have to do this for data science. In data science, all of these numbers will be given to you and you just have to compare. For example, the p-values will be given to you, the statistics will be given to you as well. When you're running a model, or when you can also do it automatically in Python. So you don't have to worry about like doing all of this calculation, but it's good to know, to see like how the process works.
Oh, I had another question. What is the graph here? Is it generally speaking, does this sort of like, to make that determination whether it's whether your hypothesis is true or not, is it like integral to have like a graph to show that? I don't know if that makes that question.
That makes sense. Like, do you need to draw this diagram to conclude whether it had an effect or not?
Yeah, yeah.
You don't have to. Very often, especially when you get to coding, instead of this, they might literally just say, okay, your Z statistic was like 1.19. Maybe they'll say even your p-value. Your p-value was 0.12. And then you have to compare it to an alpha that was 0.05. Because just with these 3 numbers, you can kind of make your conclusion.
Oh, okay.
As long as this is greater than this, you can say, okay, yeah, tutoring did not have an effect.
Oh, okay.
So this sometimes just makes it easier for people to understand what's going on. But if you don't, that's okay. Just know that large p-values usually not good.
Okay. All right. Thank you.
You're welcome. All right, let's see what's next. Okay, so we just did an entire statistical test. Those 6 steps of like calculating test statistic, p-value, leading up to interpretation, that is a statistical test being done. I'm going to send you all like, not today, but no, actually I'll send it to you all today. If you're interested in like practicing these statistical tests more, which again, not necessary. I'll send you all like a notebook that you can use, or I'll send you all a GitHub repo that you can use to like sort of test yourself if you want. Okay, so next thing we're going to talk about central limit theorem. Now the central limit theorem is actually pretty important. Not so much because we're using it in any direct way, but it's a very important concept to just be aware of, because it makes a lot of things that we do as data scientists valid. So basically what the central limit theorem is that independent random variables summed together will converge to a normal distribution as the number of variables increases. That's one of the formal definitions of central limit theorem. Another one is the distribution of sample means of any population as the sample size increases will converge to a normal distribution. This, I think, is the definition that makes a little bit more sense to interpret from a data science perspective. So let me just highlight this. So what is this saying? This is saying that if I have a population of people's IQs, there is no way I can go and like survey everybody in the world and figure out what their IQs are to get like the mean and standard deviation of IQs for the entire world. Very, very difficult to do. So instead, maybe what might make more sense is I'll grab like 10 people at a time. So let's say I interview 10 people, make them take an IQ test, and I get like a mean of 100, standard deviation of 16. I only interviewed 10 people, so I definitely cannot say that, okay, based on these 10 people, this is what the world's IQ is like. Definitely cannot say that. So instead, what I'm going to do is I'm going to repeat this process just randomly, maybe over time or something like that. And so each of those groups of 10 people, we're going to get a sample mean. And so it's not always going to be 100. Maybe sometimes if you're like, maybe you're, I don't know, outside like, maybe you're outside of college and then you interview a bunch of people and maybe they just so happen to have like higher IQ scores, then it will start to skew it a little bit. But the idea is if you keep interviewing 10 people at a time and collect the average, so you collect the average. So maybe I have like 100, 103, 101, 98, so on and so forth. Those sample means that I get over and over again will start, when I put them together, will start looking like a normal distribution. Even if the population's distribution of IQs is not normally distributed, if I take their sample means, the sample means will look normally distributed. So that's just to like illustrate what's going on. Let's just say this is the world's IQ and it ranges from like, I don't know, 80 to 150. I, by the way, don't know anything about IQ scores. And maybe instead of normal distribution where in the middle it is, what's the middle here, 115? Let's go with that. And let's just say that instead of this, maybe the distribution looks a little bit more like that. If I take a bunch of sample means from here, no matter what this blue squiggle line looks like, the sample means distribution will actually still end up looking like that. And there's actually a pretty cool lab that will illustrate this exactly. That the greater your sample size and also the more samples that you're taking, the closer and closer to a normal distribution those numbers will get to look like. So why is this important for data science? This basically allows us to use sample statistics to make inferences or estimates on the population. So again, right, like we were not able to like test the IQ of every single person on Earth, but by interviewing groups of 10 people at a time, you get like an average out of an average idea of what IQs might look like. And then it so happens that, and we'll talk about this more when we get to, I think, topic, I want to say 17 or 16, I forget which one. But basically, you can prove that this average number here is equal to the average number of the population, no matter what the population is. So that's a result of the central limit theorem. This is actually a pretty common interview question. I don't know why, I mean, I guess I know why, but you'd never have to like implement the central limit theorem in any way. It's just a good thing to be conceptually aware of. Any questions about this?
Yeah, just to clarify, when you say any population, any sample size, so it could be, you could sample 10 people and then do another sample of 80 people. Is that accurate to say?
Yeah, I believe, okay, in terms of formal definition, I don't remember if you can have different sample sizes. I honestly cannot remember. But if it's consistent, it doesn't matter if it's consistently 80 people, consistently 10 people, you still get a similar effect. I forget if when you're doing this experiment, whether you can take different sample sizes in one experiment, I forget. But I imagine the effect won't be, I imagine it would be the same. I just, based on actual definition cannot confirm.
All right. Thank you.
You're welcome.
Another question. Also,
Mhm.
there need to be like a limit on like the total sample size in general. Like you could
Yeah,
just a simple like 10 or just a simple 20, right? You have to have like,
absolutely.
okay.
Yeah, yeah. Usually the limit to your sample size really depends on your experimental design, which is something that we'll also get to. I think that's topic 15, so next week. But yeah, there's something about like the number of people that you're sampling does affect your whatever it is that you're trying to calculate. And I believe the limit, officially the limit is the population, but
But I mean,
yeah.
like on the lower end, like you couldn't have like it wouldn't be good practice just to have. So let's say you have like a group of 10 people, and then you like in my head, I'm like, oh, like that's I'm not saying
Not
guaranteed,
enough to estimate
but even if you
for the
duplicated
entire.
those just 10, like would that be a good number? Like I don't know. I feel like that was like asking for trouble.
Oh, yeah,
Yeah.
absolutely. Yeah, you cannot like generalize something that you measured based on like a small group, relatively small
Yeah.
group of people, right? Like our population is what, like 7 billion, and if we keep grabbing like groups of 10, it's probably not very indicative.
Yeah.
And there's like a whole lot of like things that you have to look for in like experimental design. I think that's something that's very similar to when people run like clinical trials. That's actually a very big consideration. Clinical trials are actually like statistical tests as well. And that's something that you definitely have to consider. Like, are your samples representative of the population? So yeah, definitely sample size is something to think about. If your sample sizes are too small, that's also not good, because you'll have a lot of outliers in that case. But yeah, good things to think about. All right, so central limit theorem is, I think the most important is just to understand the concept of central limit theorem. And I think I just said this, but yeah, there's a pretty cool lab that shows you if you have like a really weird distribution of numbers, if you keep grabbing a bunch of samples of it, the means will start to look like a normal distribution. All right. So next we're going to talk about standard error. And standard error is something that is very, very similar to standard deviation, and we'll use it for the calculation of confidence intervals. By definition, it's very similar. The higher the number, the more spread out your data is. And then the only difference is when you're talking about standard error, it usually refers to a sample. And if you're using standard deviation, it is for a population. That's one of the main distinctions between the two. I will say there's a lot of material out there that uses standard error and standard deviation interchangeably, especially when talking about a sample. But just so you know, if you see the phrase standard error, it means the same thing as a standard deviation, but usually for a sample. So as an example, if we go back to this like problem that we had set up of like the group of 40 students, here we only say that, okay, the average IQ is 103, but if she had calculated the standard deviation of this 40 students, then that would be a standard error. Okay, so the calculation for standard error, you actually just take the standard deviation divided by the square root of the number of things in the sample. So sigma is population standard deviation. So sigma here, which we approximate with sample standard deviation. So if you cannot find the, I lost my train of thought, sorry. So, right, if you want to calculate the standard error of a sample, you'll have to take the standard deviation divided by the number of items in that sample. Right, that's just something that's good to know for terminology. Okay, next, another conceptual thing that will also be just given to you in the future. So confidence interval, kind of an important concept if you want to be a statistician. For us, we'll interpret it in slightly different ways, but this is the formal definition. So a confidence interval is a range of values above and below a point estimate that captures the true population parameter at some predetermined confidence level. So what does that mean? Let's just say that we're trying to find the average IQ of the entire world. And yes, you do all of this like sampling and you figure out, okay, the mean is roughly 100. But usually when you're doing a calculation like this, you cannot definitively say that, yes, the mean IQ of the entire world is 100. Usually you're going to give it some like confidence interval or some measure of uncertainty. So confidence interval is some way to show like, the uncertainty. So the official definition, this tells you that 95% of confidence intervals constructed in this manner contain the true population mean. Now, this phrasing might sound a little bit strange. The whole idea behind this is with different ways of deciding your confidence intervals, 95% of all the confidence intervals that you're creating will create the population mean, the true IQ of the world. A definition that gets an incorrect definition of confidence intervals is that a 95 confidence interval contains 95% of the values. That is incorrect. I think that's what a lot of people, especially if you've like set with this material, I actually mistakenly thought this for a few years, which is not true. Basically, if you're asked the definition of a confidence interval, 95% of confidence intervals just contain the true population mean. For now, I know that this sounds very, very abstract. When we get to our modeling, I will explain this again in our context. So basically what's going to happen is we're actually going to see and be given a confidence interval, and we just have to interpret that. So you can calculate a confidence interval by hand. Just know that we don't have to as data scientists. You can just take the mean plus minus your margin of error, and your margin of error does depend on underlying distribution. And in this case, if we're doing a one sample Z test like we were doing earlier, the margin of error is our standard error. So all of this, the main thing to take out of this is just the definition of a confidence interval, that 95% of confidence intervals constructed in this manner contain true population mean. So yeah. I know that was very abstract. Does anyone have questions on that? If you feel like this just doesn't make sense, don't worry, because we will come back to this in our very specific context in a couple of weeks. Okay, cool. So earlier we talked about that one sample Z test. I'm going to set up the next test. We're not going to get into it. We're going to get into it next study group, but we're going to set up a t distribution. So here, when we did a Z test, we sort of knew the population standard deviation. Not surprisingly, the population standard deviation is actually not a number that we have very often. Like it's pretty hard to try and figure out what the population standard deviation is just definitively. So a lot of times you actually do not have this value. So instead of using our standard normal distribution like we did before for the Z test here, this is our standard normal distribution that we use to conduct this statistical test. We're actually going to use a different distribution known as the t distribution. So t distributions actually look very, very similar to our standard normal curve. It's just slightly heavier on the tails. So with this example here, let's go back here. In this example here, the blue line is our standard normal, and our red line, which is a little bit shorter, is our t distribution. Why that is, there's a lot of theory that goes behind it, a lot of which I never even got into because it's not important to know. But yeah, t distributions are basically used when we do not know the population standard deviation. So there's a new parameter whenever we talk about the t distribution. So remember, in a normal distribution, the two parameters that define a normal distribution are the mean and the standard deviation. For a t distribution, because we don't know standard deviation, the new thing that we use to determine or to characterize a t distribution is the mean and the degrees of freedom. So degrees of freedom is something that we'll talk about next study group in the context of a t-test. But the whole idea is the more degrees of freedom you have, the more similar to a normal distribution your t distribution will look like. So usually degrees of freedom depends on the number of things that you have in a sample. So earlier, of course, we did not do a t-test, but earlier we had a sample of 40. The degrees of freedom would be 40 minus 1, which is 39. This graphic just shows that the more degrees of freedom you have, the more similar to a normal distribution your t distribution will look like. So you can basically say that if you have a sample of more than 30, that's usually the rule, I think. If your sample is just more than 30, you can actually default to using a normal distribution, but we'll get to that more later. And the way that you conduct a t-test, which we will do an example of a t-test next study group, instead of a z-table, there is actually a t-table, which is very, very similar to this. This is a z-table. T-table looks like this, where instead of looking at the specific statistics, a specific statistic, you actually look it up by the degrees of freedom, which is DF, which I know DF is annoying because DF we use for data frame, but in this case, DF stands for degrees of freedom. And then we also talk about the kind of statistical test that we're conducting. We'll get back to this next study group, but just so you know, I wanted to set this all up. Okay, so we can calculate the confidence interval of a t distribution as well. In this case, this is the formula. You have our mean plus minus, basically the standard error. So exactly the same idea concept, but it is not important to know how exactly you calculate a confidence interval in a t distribution. Just know that how you calculate a confidence interval does depend on the underlying distribution you want to use for your statistical test or for your experiment. So yeah, this is the last slide. I understand that this is not the best place to cut it off, but there's so much more that stemmed out from here, which we will continue in the next study group. So at this point, I would say the main things to take away from today would be, first of all, the statistical testing process, not so much like specifically how you calculate all of these, but for a statistical test, what do you need to set up? What are the values that are going to be important? In this case, the test statistic and the p-value. And then also in terms of definition, central limit theorem definition, and confidence interval definition. Those are the main things to take away from today. So with that, any questions? All right, let me pause the recording here.